Okay. All right, Chemistry 102 final exam review. So again, this review was put together in order to give you a good idea on where you stand in terms of your knowledge of what we covered throughout the semester. There are some challenging problems in this review, but again, if you are able to do those, it should put you in pretty good shape for your final exam. All right, so question number 1, it says predict and label the bond angles for each carbon in the following structure. You can redraw the structure if you have to. We know that when carbon has 4 bonds, 4 single bonds, that the hybridization of those carbons is sp3. That's something that you would have learned in chemistry 101. And when carbon has 4 bonds, I have a central carbon, what's going to happen is those 4 bonds are going to seek to get as far away from each other as possible. All right, so let's say I have this carbon and I've got, the 2 hydrogens. I've got the aldehyde group. I'll just write CHO like this. And then I have the other carbon that's got all these, nitrogens, all these NH2 groups attached to it. So what's the molecular geometry of that carbon? It is tetrahedral, right? Tetrahedral. And the tetrahedral bond angle, the bond angles of the tetrahedron are 109.5 degrees. All right, so that applies for both of the carbons that I have circled in red. They both have 4 single bonds, and so both of them are tetrahedral. However, the carbon that I'm going to circle in blue, the carbonyl carbon, it has 3 sigma bonds and 1 pi bond. So it's got a total of 3 regions of electron density surrounding it. So if I draw the carbonyl like this, okay, this is my aldehyde. This carbon is sp2 hybridized, and its molecular geometry is trigonal planar. So trigonal planar. And the bond angles here are all going to be roughly 120 degrees. Again, I'll point out that the hybridization of this carbon is sp3. So again, that's something that you would have learned in Chemistry 101 at PPCC, but of course that's fundamental knowledge in order to take this class. Just in terms of thinking about bond angles, if you think back to your Chemistry 101, you would have learned a whole plethora of bond angles. What if you have a molecule like carbon dioxide? All right, it's got a linear molecular geometry, and the bond angle here is 180 degrees. So you need to know the linear shape, the bend shape, the trigonal planar, the trigonal pyramidal, the tetrahedron, so on and so forth. Question number 2 says alkanes are also known as saturated hydrocarbons. Why would that be? Well, put simply, it's because they have the maximum number of hydrogens possible per carbon atom. So we could put here, they have the maximum number of hydrogens possible per number of carbons. Right, their formula is CnH2n plus 2. I can't have more than 2n plus 2 hydrogens in a molecule, and so alkanes having that formula are fully saturated. Question number 3 says draw the line angle formula, which is the same thing as a bond line structure. So draw the line angle formula, condensed structural formula, and molecular formula for ethane, labeling which one is which. Well, let's start with the bond line formula, which I think is the easiest one. That's just going to be a line like this. This is the bond line formula. The condensed structural formula is going to be CH3, CH3. So this is condensed. And lastly, it asks for the molecular formula. And molecular formula is just the list of the number of atoms. I've got C2H6. So you need to know the difference between a molecular formula, a condensed structural formula, and a bond line formula, which I called here a line angle formula. Okay, but those are things that we covered quite a bit at the very beginning of our class, and we talked about how to represent the structure of organic molecules. Next question says, draw and name the two constitutional isomers of C4H10. So they tell us in the problem that there's only two possibilities, right? I can obviously have butane. I think that most students would get that pretty quickly. If I put the 4 carbons in a row, I have a butane molecule. However, I could make a branch like this, and I could call this molecule 2-methyl propane, which there's nothing wrong with that, right? Because you have 1, 2, 3 carbons in the main chain, and you have a methyl group on carbon 2. However, this molecule does have a common name, which is isobutane, and you probably would have seen that term, isobutane, throughout the class. Anyhow, before we name the compounds in number 5, I want to just review quickly some of the alkyl groups that you need to be aware of in this class. All right, you need to know what a methyl group is. So we have a methyl. You need to know what an ethyl group is. If you have CH2, CH3, this is an ethyl group. If you have CH2, CH2, CH3 like that, this is a propyl group. If you have CH with 2 CH3s attached to it, this is an isopropyl group. You need to know what a butyl is. So if we have 1, 2, 3, 4, this is a butyl group. If you have something that looks like this, where we have the 2 methyl groups over here, this is an isobutyl. Isobutyl. What else? You need to know the tert-butyl group. So that's this one. This is tert-butyl. And then lastly, you need to know a sec-butyl group. So that's this guy here. This is a sec-butyl group. So you need to be aware of all of these different alkyl groups, and we went over these in detail in the alkanes chapter. So with those alkyl groups in mind, let's see if we can name some molecules here. The first one, I think it's pretty easy, and I don't like to use the word easy in organic chemistry in the same sentence, but I think it's pretty obvious that the longest chain are these carbons strung together like this. So if we number those, we have 1, 2, 3, 4, 5, 6. I started on this carbon on the far left because my first methyl group is at carbon 2. If I had started over here, the first methyl group would have been on carbon 3. 2 is lower than 3, and we always go for the first substituent having the lowest possible number. So this molecule is going to be some kind of hexane because it's got a total of 6 carbons in the longest chain. I've got methyl groups at carbons 2 and 4, so this is 2,4-dimethyl, 2,4-dimethyl hexane, just like that. All right, there we go. Let's take a look at the next one. Next one's a little trickier, isn't it? But I'll go ahead and show you where the longest carbon chain. And again, the best way to find these is to use trial and error. So the longest carbon chain here has a total of 7 carbons. If we count like this, 1, 2, 3, 4, 5, 6, 7, like that. So that means that this molecule is some kind of heptane, right? We have an alkyl group at carbon 2, and we have another one at carbon 4. At carbon 2, we have a methyl group, and at carbon 4, we have a tert-butyl group. If I write down the names, I have methyl, and over here I have tert-butyl. Well, we alphabetize the methyl according to the letter M, and we alphabetize the tert-butyl according to the letter B. So now, when I put all of this together, the tert-butyl is going to come first, isn't it? So that I have 4 tert-butyl, 2 methyl, oh, I'm going to run out of space here, aren't I? 2 methyl heptane. There you go, just like that. 4 tert-butyl, 2 methyl heptane. I'm going to move this one up here just to get it out of the way. And let's take a look at this next one here. There's many ways that you could write down the longest carbon chain here. You could say, I've got 1, 2, 3, 4, 5 carbons like that. That totally works. I mean, you could do it a whole bunch of ways, and you're always going to get the same answer. This is some kind of pentane, since it has 4 carbons in the longest chain. What else? We have 4 branches, right? We have 1, 2, 3, 4 branches. They're all methyl groups. We have 2 of them on carbon 2, and we have 2 of them on carbon 4. So this is a 2,2,4,4 tetra methyl. So 2,2,4,4 tetra methyl pentane, just like that. I don't know what happened there. I don't know why my screen went dim all of a sudden. All right. Next one is just drawing a bond line structure. It says draw the correct line angle structure for 8-ethyl 2,3-methyldecane. Sounds complicated when you just take the question at face value, but let's break it down. We have decane, which is the longest carbon chain. So look, when your pen touches the screen or the paper, that's carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my chain. On carbons 2 and 3, I have methyl groups. So if we go 1, 2, there's a methyl group. Carbon 3, we have a methyl group. Then we have carbon 4, 5, 6, 7, 8. And on the 8th carbon, I'm going to have an ethyl group. So CH2, CH3. And just like that, you've drawn 8-ethyl 2,3-dimethyldecaene. All right, next question I want to ask for your participation. It says circle the molecule that you would expect to have the lowest melting point. So lowest melting point out of these 3 molecules. Could anybody tell me if I label these? I'll call this one A, I'll call this one B, and I'll call this one C. Could anybody tell me which one of these would have the lowest melting point? Remember, melting is converting a solid into a liquid. Yeah, I think you're right, Gavin. I think it is B as well. All right, how did Gavin know that it was B? Well, you need to remember your intermolecular forces, right? We start with London forces, which are the weakest type of intermolecular forces. Then from there, we go up to dipole forces, which are stronger because we're dealing with a permanent dipole in a molecule. And then the king of the castle is hydrogen bonding. That is the strongest of all the intermolecular forces, right? These are the intermolecular forces, or IMFs. If I look at the first molecule, it has a hydroxyl, so it has an alcohol, and therefore it is capable of hydrogen bonding. But if I look at B and C, both of these molecules are hydrocarbons. So these are hydrocarbons. Therefore, they are both non-polar. If they're non-polar, the only type of intermolecular forces that either of these molecules is going to experience will be London forces. But this molecule, B, is going to have a lower melting point because it has less mass and less surface area less mass and less surface area associated with it. And I went over this in detail with you in class where we talked about the surface area. And if I had, a second molecule of B, I would have 1, 2, 3, 4, 5, right, like this. And then there's a certain amount of surface area between 2 of these molecules, right, which is where the 2 molecules will experience some London forces, which holds them together. But if I had another molecule of this one, of C, since it's much longer, even though it has the same type of intermolecular force, there's just more of them that's going to hold the molecules more tightly together. And therefore, it's going to be more difficult to convert that molecule from a solid to a liquid. Question number 8. What type of isomers are the following molecules of each other? Name the molecules. Let's do the naming first. Remember that when you have 4 carbons in a cycle like this, so if you have 1, 2, 3, 4, this is a cyclobutane. And thus, the first molecule, both of the methyl groups are on the same face of the molecule. So this would be cis 1,3-dimethyl cyclobutane. And the other molecule would be trans. So this is trans 1,3-dimethyl cyclobutane. Could anybody tell me what type of isomers these are? And it's not a trick question. What would be the best description? They're not constitutional isomers because constitutional isomers are when we have two molecules with the same molecular formula but a different connectivity. Both of these molecules have the exact same connectivity. The way that they differ is the arrangement of atoms in space. Exactly. So these molecules are stereoisomers. Stereoisomers because they differ in the arrangement of atoms in space. Atoms in space. Like that. So stereoisomers would be the best answer. There are also diastereomers, but I'm not really going to ask you much about diastereomers. It was something that we just mentioned very quickly. Let's see. Next question, number 9. It says, write the condensed structural formula of 3-nonene. I like to solve these problems by writing out the bond line structure first. I honestly find it easier to do that. So I'll say, if I've got 3-nonene, I've got 9 carbons in my molecule. 1, 2, 3. On the third carbon, I've got a double bond. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's the bond line structure of 3-nonene. Now, if I want to write a condensed structural formula, I have a CH3, then a CH2, then a CH, a double bond, then another CH. Then I've got 1, 2, 3, 4 CH2. So I'm going to put those all in brackets. I'll put CH2, 4, and then I have a methyl group on the end. And just like that, we're done. Question number 10, name the following molecules. These are different molecules, aren't they? They both have the same molecular formula. They have the same connectivity. However, one of the molecules is a trans compound and the other one is a cis compound. The first compound is the trans compound because the two hydrogens are on opposite faces or opposite sides of the double bond. And this molecule is a cis because both of the hydrogens are on the same side of the double bond. If I number both of these, 1, 2, 3, 4, 1, 2, 3, 4. Again, they have the same connectivity. However, one is cis and one is trans. And so if I name the first compound, this would be trans. I've got a bromine on carbon 1, so trans 1 bromo, 2 butene. And the other molecule would be cis 1 bromo, 2 butene. And not only are these compounds stereoisomers because they have the same connectivity but different arrangement of atoms in space, but you could also say that they are geometric isomers. Okay, geometric isomers because it's just the shape of the cis-trans bond that results in them being different molecules. So you could also call these geometric isomers.